Hello, guys. Welcome to today's live stream. So this is a live stream from Tuesday. I was not able to do due to a lot of technical issues I had um, on that day. So I just had to cancel the whole thing and then do it today. And also today, I also almost did not do this, but that was basically main due to my own personal issues that I had. I tried my possible best to make sure that I'm here um, today. So, guys, welcome once again. Give me a moment. Let me quickly do something. Okay, so yeah, let's quickly do something. So, guys, once again, welcome to today's live stream. So, please, if you can hear me, consider dropping a chat in the comments. And if you're on Twitter, please consider retweeting the live stream. So on my screen, there should be a yeah. So this is the live stream stuff. So consider liking, retweeting. I have about 7 persons here, um, and 2 persons on YouTube. So please consider retweeting this, liking, dropping a comment. It's not that difficult, right? So yeah. So once again, I'll say thank you guys for joining me here on the live stream, right? So I really appreciate you guys always showing up for these live streams. So without further ado, I would go into today's stream. Go into today's stream. So so today we're going to be talking about trees, right? It's a data structure. The data structure in most programming languages, right? In all programming, in fact, in computer science, right? It is a data structure, and basically, um, we're going to be looking at how we can traverse it, right? How we can traverse this data structure in three different ways. I think some days ago I made a tweet about tree traversal. Some people in that tweet got what I was talking about. It was kind of a vague tweet, and the major purpose of the tweet was to provoke a discourse, right? Um, yeah, was to provoke a discourse around the subject. Um, but yeah, some people got it, some people didn't get it. But at the same time, um, it's one of those data structures that I said I was going to talk about. So today we'll be looking specifically on how to implement depth first search, so DFS. And if we have enough time, I also look at breadth first search. All this we'll do it, or we'll do all this in Rust. So this particular live stream is the part 1. If I'm not able to, due to time, because my live streams are usually too long. Um, if due to time I cannot go over to binary first search, um, then we would have a part 2 for this, right? And in that part 2, I would just focus specifically on um, BFS, right? So there are two of them. We have BFS, and then also have DFS, right? Um, so yeah, I think that's it. Um, so what is DFS, right? Or okay, first things first. Let's talk about trees, right? So a tree basically is a hierarchical data structure that is made up of nodes, right? Where each node contains a value and pointers, right, pointing to left and right, something like that. So we just take a look at a Wikipedia um, you know article on the subject. So basically tree basically is an abstract data type according to this Wikipedia article. So it goes ahead to say in computer science, a tree is a widely used abstract type that represents hierarchical data tree structure. So basically, it's a tree, an inverted tree, right? In a real world sense, this node here would be the roots of the tree, while all these guys would be the branches, right? So it goes ahead to say with it's a hierarchical tree structure with a set of connected nodes, right? So all these circles here with values in them is a node, right? So each node in the tree can be connected to many children depending on the type of tree, but must be connected to exactly one parent, except for the root node. So the root node is, this guy here, the root, right, which has no parents, right? So it goes ahead to talk about binary search tree is a commonly used type which constrains the number of each of children to each parent, which to be at most two, right? So you get the idea. So the basic thing to understand is that it is an ADT, which is an abstract data type, which can be represented in a number of ways, including um, a list of parents with pointers to children, and a list of children with pointers to parents, you know, or list of nodes and separate list of parents children relationship, where we have something like an adjacency list. Um, so it goes on and on and on and on, right? To talk about just basically theoretical things, theoretical things that you can look at. So we have trees and non-trees and and all that, right? Also goes ahead to talk about traversal, right? This is basically what we'll be talking about, right? Post order, pre-order, and in order. I even made a tweet about this sometime where I made a tweet where I was talking about tree traversal. So I think let me check if I would see um made a tweet about this. Um okay, where is that tweet? Oh, I tweet a lot. Okay, so yeah, so I made this tweet. Oh, sorry about that. Uh, yeah, so I made this tweet where so guys, if you heard a weird sound in my mic, oh okay, I will send you my YouTube link. Sorry about that. Um, hold on, let me send you my YouTube link. Okay. So hold on, guys. Let me drop my YouTube link on here for those that wants to see it from YouTube. So for some reason, um my my Twitter streams are always really, really, really low quality. I don't know why this happens. I guess it's from the streaming software I'm using. But that, uh, and then that should not be an issue any longer. But for now, please, you guys should manage me the way I am. So I'll be dropping a link to the live stream on the chat. So please let me know if you can see that link. If you can't, I would also drop it here on Twitter. Mhm. So if you check on the Twitter chat, you should be able to let me see, check on the live chat for check on the live chat here. You should be able to see a link to YouTube. All right. Okay. So yeah, back to what I was talking about. So we have so basically that's you can basically dive into more theories about this on your own free time. But basically um it's just a tree that is inverted, right? So if you check pictures of trees, so picture of trees, so it's just like a normal tree, something like this, right? That is turned upside down, right? So let's say this root here, the root here was turned upside down. So you know that we know that this tree has branches, right? So it's the same concept here, right? So it's an inverted tree, right, that is turned upside down. Oh, okay. Thank you. I didn't even know that. I didn't even know that it was completed. Okay, thank you. So, guys, please consider dropping a comment. Sharing this live session with people, so that more people can join and get the knowledge. So, back to what I was saying. I'm looking at the picture of an actual tree. It's just an inverted tree, just like they uprooted this tree and turned it upside down, right? Turned it like this. So that's why it's actually even called an abstract data type, right, in computer science. So that's what we are going to be looking at today, right? We're going to be looking at how we can create this in Rust and how we can traverse it, right? So back to what I was saying initially about what's it called, about the tweet I made. So there are three types of tree traversal. So we have the pre-order, which starts from the root node to the left and the right. Then we have the in order, which starts from the left and goes to the roots, then the right, and the post order, which starts from the left, then goes to the right, then goes to the roots. Right. So I made a tweet about this some days ago. I was talking about it before. I got distracted. I wouldn't really say it, I got distracted. I'll just say I had to send YouTube link. I can't find this stuff again. Mm, some days ago. I don't want to waste much time here looking for something. Okay, yeah. So this is it, right? So this is the tweet. It basically says roots left, right, and it says left, root, right, and it then goes ahead to say left, right, and root. And basically, this is just how I recall it, right? So this is pre-order, in order, and post order, right? So a lot of other people went on to you know tree traversal, and other people went on to leave comments and all that. And this person really said something, graph traversal, which I was really impressed. Um, give that a like. Yeah. So guys, once again, I'll say welcome to my live stream. This stream was supposed to happen on Tuesday, but due to my technical issues and challenges, I couldn't do it. So here we are today, um, Thursday, and I'm glad and I'm happy that I've been able to resolve all my problems. And so let's get right into it. Okay, so if you have been in my last stream, um, you'll notice I've made a lot of changes. So every data structure that we implement, to the point where we get to algorithms, we'll do them in different files, and we'll use the main.rs file to kind of um, you know link all of them together. And so the reason for doing this is just to have a single place where we do all these things, and it's neat, right? um yeah, so that will make it neat and enable us to have a repo where I would push all these things to for those that are interested to really dissect the code to understand what um is happening and all that. So today we are going to be looking at so let me comment out linked list. So we'll be looking at you know building a tree and save these. And so there is a command for removing all those warnings. I think it's allow dead code. Not sure. Allow dead code. I guess so. I don't know. Hmm. I don't know why that's not working. Anyways, let me comment this out. That's not the purpose of this live. So now I'll just go ahead and close some of these guys. Close this. I don't need them. Close the queue and close the tree. So now the first thing we'll do is let's think about it, right? How do we create this guy? Just we need first of all we need to create a node. How would we represent like a binary tree, right? In Rust. So we know that every node has takes a value and has two pointers, right? One pointing to the left and the other one pointing to the right. So we have to think about it. How are we going to represent this? How are we going to implement this in the code, right? So what we'll do is we'll use structure. I've used that a lot, right? So we'll use structure and we'll give it a very interesting name. So we'll say tree node is going to take a generic. So I'll explain all these things. I'll just quickly write out the code. And in there, um, first things first, we know we have a value. So in this case, we have value of 2, and we want something that would represent the one that is pointing to the right and the one that's pointing to the left, right? So here I would say value, and would type t, then left, and left to have an option. So I'll explain what this option is. It might be confusing, but I'll explain. Then we have box, and in there tree node, where we then pass value of t. So I'll just copy this guy and right. Okay, so I'll save this. So um we've created the structure, right? The structure of how this is going to be. So this is the value. So in this diagram we have here, that the value is going to be 2. Then left and right are these arrows, which we just did here. So basically, if you take a look at this, T stands for generic in Rust. So we go generics. Let's pick the first one. No, this is too comprehensive. Let's go to Rust by example. Yeah. So here, you can immediately see it, right? So it says generics. Okay, the type parameter used to specify um is a type parameter is specified as generic by the use of angular brackets and upper camel case, right? Generic type parameters are typically represented as T angular bracket T angular bracket close, right? So in Rust, generic also describes anything that accepts more than one generic parameter. So what this means is can accept a number, a string, a boolean, a float, whatever, right? So that's like what it means. So that's what T means. Right. Then looking at options, so option, we use option to specify that the node might not always have children, right? So take a look at if we go back to our diagram here, and we can notice that this node here, 5, has only one child, right? If you look at this one here, 2 doesn't have any child at all. So that's where option comes into play, right? So when we use option in the code, we are saying this node might have a child or it might not have a child, right? So it represents that situation where we have some value and when we have no value. Then box, right? Box represents how Rust stores data on the heap. And so that's like a more um, you know, complex topic to talk about. But basically, we have the heap and we have the stack, right? You can actually dive deep into that. But basically, Rust uses box to store data on the heap. So basically, at the end of the day, we are now wrapping. So the box in this case is kind of like I would say a smart pointer, right? That wraps our tree node, right? And at the end of the day, um, stores that value on the heap. So we can still go back to the documentation and let's just say box. Let me say box Rust. Let's see what we can get. Box std. Let's see. Okay, so checking. I'm looking for an explanation that says something about heap. Okay, a pointer type that uniquely owns a heap allocation of the type T, right? So storing things on the heap. So you can actually look out, can check out the difference between stacks and heaps. Heaps. think I even have a video of this. So this is I want to use somebody's article, and they will end up I don't know. Let me check geek for geeks. So we can go ahead to look at stack allocation. So remember in our previous classes, let's say streams, we talked about stacks, right? How stacks work. We even implemented how it works. We even implemented um, you know, that data structure. So it's similar to what we'll be seeing in this place, right? So I'll just focus on the diagram if I would even see any here. Can't really see this well. It's not bright. Weird. What kind of color are they using here? Anyways, I think it's the Geek for Geeks color they are using here. Uh, can't see something like I reference. Anyway, so this is stack, and then this is heap. I don't understand. I don't understand this. Can't even see it well. Anyway, let's just move on. So basically, that is how we are using to create like a single node. Um, you know, a single node that will represent our tree, right? That would be part of our tree. So we'll go ahead to create a constructor, right? So we'll create a constructor that will enable us to create nodes easier, right? And the way we do this is we use implementation. So there's IMPL. So we'll pass the generic type of T, and we'll call these three nodes. So same name, and pass that T again. So this is just syntax. And in here, we'll define a function that we would call new because we want to create a new node all the time. This function is going to take a value. There's going to be a type, generic type. So pass T there, and it's going to return self. And in there, we're going to call three node. We're going to say value, and then left. So left would now none. So this none is coming from the option type here. So we'll get to that. Have right, which is also none. Right. Yeah. So that's basically, so this would enable us to easily create new nodes in on our application. Right. So now what have I done? All right. Okay, now so we'll go ahead and talk about the DFS, like how we can, traverse um, our tree. So basically, we're going to use the recursive approach. There's also an iterative way of doing this. The iterative way of doing this is very good, and I would say, in my opinion, is um, a preferred way of doing it, especially when you have a large number of data that you want to check on the tree, right? So we are going to um, basically do this today um, in a recursive manner or recursive approach. And then so basically the DFS in this case is depth basically depth first search. And what we are doing here is we are exploring all the possible branches on the tree, right, as deeply as possible. Um, then we'll then backtrack at the end of the day. And like I mentioned earlier on, there are three types. So I even pulled up a tweet about that. I made a tweet about this. So there are three types. So the first one here is the pre-order, where we start from the roots, then we'll go to the left and the right. The second one is the in order, which is left, right, left, root, and right. And the last one is the post order, right? So if we look at this here, we have if we want to do something that has to do like the pre-order, we'll start from the root. We'll get to the algorithm will go to the root first, and from there we'll go to the left, then we'll go to the right, right? If we are doing in order, we'll start from the left, then we'll go to the root, the right. If we are doing post order, we'll first of all start from the left, then we'll go to the right, and then we'll go to the root, right? So these are just the ways that we traverse the you know the tree. So first things first, we are going to write a function, and we're going to call this function. We're going to write three different functions. We're going to write a function for pre-order traversal. We're going to write a function for in-order traversal. We're going to write a function for post-order traversal. So basically, we start the same way. So we call this pre-order traversal. let me just say trav. And this function is going to take two things. It's going to take the root and it's going to take results. And this result is going to be a mutable reference to a vector, which is going to have a generic type, right? So let me just write the code. So we just say roots, and this roots is going to take sync option. Just want to handle case where there is none, and reference to three node. That is going to take. Let me close this first. Generic type of T, right? Then the next is going to be result. I call this result. I'm going to take a mutable reference to a generic type of T. Right. So we have this. So this is going to be basically the same format for the rest of our functions, right? So I'll just as well go ahead and let me just leave that out and let's write this out, right? So first things first, what we are going to do here is we are going to check if the root exists. If it does, we'll extract the value from inside of the root. If it doesn't, we'll just pass none. We'll also clone the value. I'll explain why we clone the value, or the reason why we clone the value is because we're passing it as a reference. And due to Rust ownership rules, if we don't clone it, the code will not compile, right? So also at the end of the day, we'll also deref, which would enable us to convert this option box into something that we can recursively traverse, something where we can recursively move through, right? So I know I'm speaking a lot of grammar, but I'll just go ahead and write the code, and later on I'll come back and explain them one by one. So the first thing we'll do here, like I mentioned, um, first of all, we say we need the roots, right? And yeah, so here would say before we do that, we want to check if there's a value in the root, right? We want to check, so we'll use an if let. Okay, if what am I writing today? If let's some. So we'll pass in our node here because we are extracting it, kind of like the structure, right? I don't know if that's the right word to use for it. I would just say it's kind of seems like just like the structuring. That's how you can relate to it. So I'll pass node. This can be any value, but I'll say node. And yeah, that's basically it for that. Then in here, I want to follow the pattern, right? So I know I'm doing something that has to do with pre-order. So I'll add a comment here. I'll start from the root. Then from the root, I'm going to go to the left. And from the left, I'm going to move to the right. So first thing I'll do is I want to push a cloned value into my result, into this result here, right? So I'll say result dot push PSH. I'm going to say node, which is our node that we have extracted from here. Node dot value, and we want to clone because remember, due to Rust ownership rules, we are already referencing. So if we don't create a new copy of our node, we will have a compile error. It should not work, right? So just say node dot clone, and I'll call that function here. Save this. So this is the first part, right? So with this, we are visiting the root. So I think am I getting that error? Not found for type of T in the current scope from traits can only be used in parameter and bound trait, blah blah blah. Hmm. Okay. Okay. I'll come back to that. Let's just move on. So here, this is where I'm going to do the whole what's it called? Um the whole recursion stuff, right? I don't know why I'm having issues remembering that today. So we're going to call this so basically a recursive function or a recursion is a function that calls itself, right, to do something. So we'll say pre-order order trial. So this pre-order trial, in it we are going to pass the node, so the left node, because we know we want to visit the left first. So we say node dot left, and we want to deref it. So we say as deref, right? So okay. Mm, Expected full stop. Okay. Out of found operator. Okay. Then here now we're going to also do that same thing. So we'll say pre underscore order trav, and we'll go to the right. So node right as ref. Okay. Result dot push node value, clone that value. So we're visiting the root here. Add the comments. Visit roots. So this would be our left. Only ft, and this would be our right. Yeah. So guys, please once again I would want to say thank you for joining on this live stream. Um this live stream wasn't planned, to be very honest. I didn't plan it. And seeing this number of people on here, I'm really happy, to be honest. That you all have taken time out of your day to come join me on here. I really appreciate it. Please remember, you can always um, you know ask questions in the chat, right? You can always ask me questions in the chat. Um, you can even see the stuff on your screen and ask questions in the chat, or you can just whatever to get this out to more people who might be interested in what we are doing here, right? So once again, I just want to say thank you all, and always remember that um, I'm trying as much as possible to make this like seem like a dialogue where we have conversations. I make mistakes, you can pick it up and correct me. I honestly do not know everything, right? I don't know it all. Um, for being here. Um, yeah, so that's basically it. So I'll just get back to it, but please consider dropping a comment, sharing this, maybe retweeting it on Twitter. Just anything to support what I'm doing here. All right, so I think let's just get back to it. All right, so we are just implemented now is the pre-order traversal, right? Like I had explained before. This traversal moves from the root to the left, and from the left to the right. I'm having all these weird errors. Save this, right? So it moves from the root to the left and from the left to the right. So from root to left, from left to right. So this is um the first way of doing it. So we'll go ahead and implement the second one. Uh, Node dot value clone. Still don't understand why I'm having these errors. I will get back to that. So the second one now we're going to look at is so I would add a comment here for this um in order traversal. And I'll add another one here. Sorry, this should be pre-order, not in order. Because pre-order goes from the root to the left and the right. Then in order goes from the left, then to the root, and then to the right. Uh-huh. So okay, okay. Yeah, so back to it. Like I mentioned before, we we use the option here, right? Because respect that we know that it's not at every time or at every point that our our nodes are going to have roots. So there are situations whereby a tree might be empty, right? So in that situation, we can handle that with none, right? We'll just return none. The situation whereby we get a value, we can handle that with some, right? Something like this, right? So that's why we do this. We wrap everything that we do with option type, right? Then for the if let, so I'm just trying to explain everything. So the if let checks if the root exists, right? So in a situation whereby the root exists, what we do, we go ahead and extract the value here. So if there's a root here and there's a value there, we'll go ahead and extract that value, right? Then for the node.value.clone, so the value here, right? This value is passed as a reference, right? It's passed as a reference to our function, right? So passing it as a reference to the function, if we don't clone, if we do not clone, would have an issue, would have like errors, right? Because of Rust ownership, since it enforces these very strict borrowing rules, right? So now this part where we have node dot left dot as deref, um, what it does is it makes it easier for us to recursively traverse without worrying about ownership, right? It enables us to traverse the tree without worrying about um, ownership, right? So yeah, that's basically what every line of code here means. And the reason I'm taking my time to explain this is because the rest of the code is going to be um, very similar to what we had already done, right? It's going to be very similar to what we had already done, and this is because the only difference is that we are just going to change the structure, like the order of how we, how we, push into our vector, and then how we, um, you know, recursively call the functions itself, right? So that's basically what we are going to do here. So I wonder why I'm having this error. So no method clone found. 30. Mhm. Mm. Okay. So let me try something different. Root function. Hmm. This is a reference. Okay, let me see. Do this. So what happens? Not find product trap. At this point, I think this is just crazy. What do you mean you cannot find the function when this is the function? Let me run this first and see what happens. Hmm, Save yourself. Oh, I see. You're using the associated function. Okay. So Rust is telling me that this method is not found. I can include this in my implementation block, and I should consider using self. Okay, let me do that. So clone. Okay, and I would self same thing for here. Self other. Okay, not found in this scope. Okay. Mhm. Oh, I see. Yeah, I see. I see. I see. I see. I see. I see. So that means I don't even need to necessarily need to include this guy. So take this out, and yeah, so this function is expecting a second argument, which is result. I wonder how I did not see that. Results, and here results. Okay, exactly. Clone. Uh, I guess I better put back my clone traits here. Clone, save, and yeah. So yeah, so I had to figure out what my issue was, and then so I'll go run again and see. Yeah, so I don't have any issues. I just have warnings. Associated functions, new and pre-order are not used. So these are just warnings. Okay, so it's funny how I kind of missed the second argument, passing the second argument to the recursive function here. And I guess at this point I don't even need self. I should work without self. That's just you know first place. So cannot find function pre-orders. Okay, so I need to reference self. Right. So that makes sense. Okay. Yeah. Okay. Okay. That was really um challenging how missed that. And guys, the that's like the whole thing about coding. Sometimes you make this kind of mistakes and stuff. But this was a funny one. So, anyways, I'll clear this and let's continue. So we'll move over to the next one, which is in order. And basically, in order is very similar to this, right? The only difference is just in how we, you know, how we move in the data structure, right? How we move in the tree. right? So in the in order, we would move from the left to the roots and from the roots to the right. So I'll just copy everything here because of time, paste it here. And remember, if you want to format your code, so you can just do cargo FMT today. I don't know what's happening. Cargo FMT and it formats everything for you in a clean, nice way. I'll clear this. And here I'll just change the name to in order. In order. Um so it still takes an option, the reference to the tree, and the generic T type. Then the second argument, which is the results, which is a vector of generic type of T. And then we'll then recursively call function. So yeah, Control D, and V. Then I'll take this guy out because we know our 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 traversing pattern here is we first of all go to the left. So let me update the so this is the left, then from the left to the root, then the right. So we'll first visit the left here, then secondly we'll go to the root where we do our node clone, and after that we'll then go to the right. Right. So we'll still do this for the post order traversal. So copy everything here, and just because of in the interest of time, so I'll call this. I'll say post order, and I'll change the name to post capital letter, just small letter, post order. Still takes the root and the results. The only difference now is that the order in which we are, um, you know, traversing changes once again. So this time around we have left, and from the left we go to the right, and from the right we go to the root, right? Um, yeah. So then I'll copy this guy and change this to the and I'll take out the result dot push and pass that guy here and save. Once again, cargo FMT to format everything. Yeah. So I just have a couple of warnings telling me that I have associated functions. Um, associated function new pre-order, in order, and post order that I have not yet used. So now we'll go ahead to um, to use this particular functions that we've created. So these are like constructors, like constructor functions we've created on the tree node itself. So if you remember, the tree node is a representative of a node, right? From our diagram, we know that every node has a value and a left and a right pointer, right? That points to a child that also has pointers, and it keeps going on like that. And we know that there are other types of trees. Like for instance, we have a binary tree, which is constrained to having not more than two children because of the word binary. Binary is two, right? But back to this place, we've then gone ahead to implement a function that enables us to create a new node, right? Then we've created functions to traverse the node and do all that. So what we'll do now is I'll go ahead and we already have I'll go ahead and put things in the node in our tree. So we already have like what's it called? We already have a function called build tree, which we are importing into the main function. And so just basically a way of making our working environment cleaner and you know and neater, right? So we already have that function, and the function would help us do whatever log we want to do here in the terminal, and without having the need of having all other data structures in one file and complicating everything. So back to this place here, the first thing we'll do is we'll first of all, um, you know, initiate or instantiate a new node, right? Remove that caption. Okay. So we'll remove that caption. And so first off, we'll say let's create a root, right? To say let's mute root. So it's tree node. So tree node, which is this, and we'll call the new function that is implemented on this. So three nodes and new, right? So this new is going to take our first value is going to be one. Let's just pass one there, or we can do 10, right? So and this, so this first value is going to kind of be like this guy here that we have this place we have two as the root, right? So on this root, we are now going to be able to access root dot left, right? Because we have this, and also root dot right, because we have this. And there we are now going to, because we know we have this, and there we are now going to place values inside on the heap, right? So we're going to place values on the heap. So we know that on our left and right, we have option, and this option returns two things, as you can see, none and some. So for none is when we don't have any value, and some when we expect the value. So we are going to wrap the data we are going to be passing onto the left or the right. We're going to wrap it in some. Then we know we have our box, so we're going to create a new value on the heap, right? The way we do that is box new. So if we come back to this place and we'll go to box docs rust. So let's see how we can use this to create a new um, value on the heap, right? So hold on, guys. Let me hide this. So here, go on and go on. Let's just read. So we can see here on line 24. We'll do something like this. So box new, and in our case, we'll pass our three node, and that our three node we are also going to create a new node because we want to create a new node. So we'll do three dot new, which is how we can create a new node, just like I just shown here, right here, which is the root. So we're going to do this inside our box. So in order to create our data on the heap, we're going to do something like this box new, and then we are going to wrap it with some because this this option returns two things, right? Which is some or none. So we know we want a value there, so we're going to wrap it in some. So I'm trying my possible best to explain this in the best way I can so that it's understandable, right? It can really get confusing and a lot ambiguous in a short time if one doesn't really explain it. You know, I can just quickly gloss over it. Of course, I know what I'm doing. I can just gloss over it and move on. But then again, it wouldn't be helping, um, you know, the viewers like you guys who are, viewing and all that. So I'll just go ahead and explain and code out what I just explained. So we had already defined the route, which I just showed. So on that route, we know we have access to right and left. So if I hover over it, I should be able to. Oh, I'm not seeing anything here. Anyways, I'll just do routes, right? Dot. I will see left. You can see I have left, right. So root dot left. So I want to go to the left first. And in that place, I want to add a value to it. So I'll wrap it in sum, which is coming from options. And I know that in my options, I wrapped it in a box. So I want to create a new box. So I'll say box new, just like we saw in that documentation, box new. And in the box new, I would to wrap again. And in the box new, I want to create a new node, right? So how do we create a new node? Similar to how we did it in our, what's happening? Similar to how we did it here online. What's happening? Similar to how we did it here on line 48, where we created a new node. So we're just going to do that same thing inside the box new here for the left node. So we'll say three node, three node, and new, right? We created an associated function called new, right? So there we're going to pass another value and we'll call this 20, right? So this is how we would create child values, right? So it's just basically the structure of what we had defined here, right? So just the same thing, right? In the left, we have option, which is returns two things, some and none. We have box, which we use to allocate the data on the heap. So if we want to do that, we'll say box new, and we have the tree node. And the tree node we created a function which enables us to create a node, right? So there we are now going to pass the value, right? And we're going to append it to the root dot left, which is the root, which is in this case, looking at this, going to be two. So to the left, we have appended 20, right? So that's exactly what we did there. So we'll go ahead and do the same thing for the right. So say root right I'll just go ahead and code this out quickly. New, and in there I have my three node, another new function that we originally created, and I'll call this 30. And yeah, so I'll just do that. And with this, we've been able to create a what's it called, a tree, right? That's seems something like this. So let's say I have this, and let's say I've created a tree that's like this. I'll say this is the roots. Roots. Call this this case 10. 10, right? I'm trying to create a diagram here. So this is the root. Down here, I'll use something like this. So trying to create this. So this is another arrow. Then we'll have another one pointing to this side. So, and then down here, we'll have the next value, which is 20. 20. These are the child, and would have 30 here. So this is what we had just created. Right. I can go ahead and give these two parents their own child. So when they have their own child, they automatically become parents. Right. I can go ahead. So, but basically, this is what I just did here. Right. So I'll go ahead and root, and let's go ahead and try to you know print what we have to the terminal. So I'll just write some code quickly because time is not on our side. So I'll say root dot left as mute dot unwrap. To unwrap this left, and I would say some tree node blah blah blah. So basically, what I'm doing here is I'm creating a child, right? So other child is for know the root node, right? For the left root node. I'm trying as much as possible to explain this in such a way that it's understandable, right? So I would use this diagram to explain everything that is happening here. So let me just quickly write out the code. So I'll say um no need of writing out everything again. So I'll just copy this, paste it here, right? Yeah, so some box new three node blah blah blah. I'll call this 40, and I'll do the same thing for, yeah, so this is for left, and probably I'll do the same thing for right, or I'll just do the same thing for left again, right? So I'll copy this it here, and I'll change it to 50, right? So I'll change it to 50. Then, so basically what I've done here is in the left node, I've gone ahead to kind of like, um, no, not left. This should be right. So I want to add to the right. So, so this left node, which is 20, I've gone ahead to, oh God, what's happening today? I'm gonna head to add I'm gonna add two children on that guy. So I'll delete this, and here I'll say what I did here is here I added 40 to the left, right? Add 40. and um, added 50 here. So I'm trying as much as possible to visualize this as much as I can, right? So basically, what is happening here is we have the roots, which is 10, which you had find here, right? And then I have the left, which is 20 and 30. Then in order for me to append a child to this um you know child node, which is a child to 10, I had to go into root dot left, and this is mutation. So as making it mutable, after everything I unwrapped it, and to the left added another value again, right? And yeah, so that's you know basically what happened there. So I did the same thing for the left, which is this guy, and I added values to the right and the left. If I wanted to do the same thing for this guy, which is 30, who is on the right, I would rather go ahead and do root dot right, dot as mute, dot unwrap. Then I will add a value for the left and do the same thing for the right. Like you get the point, right? Yeah, this whole thing can really get complex. But I'm trying my possible best to explain it the best way I can. Right? Believe me, I'm trying my best to explain this the best way I can, uh, so that people can get to understand what is happening here. It can really get confusing at times, even for me myself, that I'm doing it anyways. So I'll then go ahead and let me go ahead and log. So I'll say let's mute that's the results. So results sorry yes t and I would say I want to create a new vector. So so vector new. So this is coming directly from Rust. And here I will then call our pre-order. Let me call the pre-order. Hmm, no, 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 no. Hold on. A mhm. Let's say tree node. Okay, tree node dot pre-order, and I'll pass the root, right, which is going to be sum. So sum, and it's going to be a reference to the root because I don't want to take the ownership of that root. And I'll then pass immutable reference to my result. So the result, and I'll save, right? And at the end of the day, I want to create a print line statement, and in there I'll just say this is an in order, and for this result, and let's see what happens. See what happens when we do cargo run, if everything would dismantle. Exactly. So we have the in order. So one of the applications of the in order traversal is, I think it's for sorting. It can be used for sorting or looking for things in order, something like that. Right? Yeah, I guess so. Um, what function did I call here? Is it pre-order or in order? This should be pre-order. Pre, right? So if I go ahead and check some use cases pre-order DFS, when searching elements within a binary. So this is coming from AI. So pre-order DFS is commonly used to create copies of tree, generate prefix expressions from an expression tree, and effectively search within a tree structure by first processing the root node. Before exploring the children use cases, building expression tree, copying a tree prefix, searching in a tree. with a root dependent decision, database indexing, blah blah blah, to determine such a moral ID data inject, blah blah blah. I'm not seeing anything here. What is the use cases of pre-order traversal used through traversal algorithm to suggest pre-order each node um, for its child. Process print nodes. Blah, blah, blah. I've not seen anything here, but yeah, there are some real world use cases, right? Like database indexing, searching in a tree with root dependent decisions, prefix expression generation, copying of a tree, right? And building expressions from a tree. There are more of this, right? There are more of this. There are more of this. But let's just move on. Yeah, so we have this logged. So we have 10, 20. So if you take a look at it, we have 10, this is 20, 40, then it goes to 50, then it goes to 30, right? That's how um it works, right? So we'll take a look at this, goes to the roots before it goes to the left and finally the right. So the root here is 10, another root here is 20, then 40, then we go to 50 before we go to the right, which is 30. And that's how we've logged it here in the terminal, right? So we'll go ahead and do the same thing, um similar thing for the rest of the functions that we have, right? So in order to move forward, we just go ahead and so let's do results dot clear just to clear everything, and we'll just go ahead and do the same thing here. So take this, paste it here, and I'll call this posts or in order traversal, and I'll rename this in order save. uh, so let's run this code again and see. Cargo run. Okay, exactly. So now that we are now in the in order, so remember that in the in order, um the in order algorithm, we first of all have to visit the left before we visit the root, and then we visit the right, right? So we have then we'll visit its root, which is 20, then we'll go to the right, which is 50. So if you take a look, let me increase the size of my terminal. Yeah, I don't know if it's easier for you guys to see. Try as much as possible to make it large. Close this guy and pick this up to this point where you can see all this. We take a look here, right? So for the in order, remember for the in order, we go from the left to the root, then to the right. So first thing we have here is 40, right? So we have 40, which is at the left, and we're going to the root, which is 20. So if you take a look at vector, this vector is kind of like similar to arrays in languages like JavaScript, right? The only difference is that vectors in Rust they don't take different types, right? So an example of this is, sorry, I'm digressing, but let me just show you guys something. So here, if I pass instead of 20 and I pass something like true, which is a boolean type, I save this, right? I would this would break when I run the code. This would definitely break. To say mismatch type, integer, expected an integer but found a boolean, right? That's because vectors, when you define a vector, it takes only one type. It's either it's taking only booleans, or it's taking only integers, or it's taking only floats, right? So where did we define that? So this is one place, right? Say that what we are always going to expecting as our result is going to be a vector, and we also did that here, right? um where we said let the result be vector new, and it's part of what we passed into our functions. So it's automatically expecting a vector type of I32s because we did not define any vector type. So it's just going to take the type of I32, right? So passing something that is not an integer here is going to crack the code, it's going to break the code. If I also pass something like a float, like 1.3, and I save this, it's not going to say the same thing, right? Mismatch type, expected integer found floating point number, right? So I will just go back to what we had before. So now looking at this again, sorry for the digression. We visited first of all the left, which is this guy. Remember, it's depth first search, so we go deeper, right? So depth first search. So we start from you know this part. So visit the left, and from the left we go to the root. From the root we go to the right. Then we then go to the root again, right? Because we visited everything on the left, so we start from the root. Then at the end of the day, we end up at the right. So let's go on again and do similar thing for um or post. So here result.clear. So this would be post order trav. We'll also pass our roots, right? So the roots represents everything we've passed into our tree, while the result represents our vector, which I explained that seems like works similar to an array in JavaScript or any other language, but just that it doesn't take more than one type. Right? So pass our result here, which is a mutable reference, and then yeah, so we're also printing, so we'll just call this post order post. So in this case, we know we'll visit the left, then the right before the root, right? For post order. So I'll save this and I'll run this code again. Cargo run. Uh-huh. Get exactly. So if you take a look at it, you see these are the roots, that is the child, the children. So we'll visit the left first. So the left here is 40. We will have 40 logged here and printed here. Then we visited the right, which is this. If you remember from the function that we had created here, we said we'll go from left to right, then the root. So we visited this guy, Travers, and we got 40. Then we went on to 50, which we have here. Then went to the parent, right, which is 20, which is the root. Then from there, we'll then go once again to the right because we don't have anything on the left. If that we had something on the left, would have visited that, but we'll go to the right. Then finally, we'll now go to the root, which is 10. So, guys, that's basically everything. If we had more time, I would have actually gone ahead to implement um, um, binary first search. So, sorry, breadth first search. Sorry about that. I would have gone ahead to implement breadth first search. So, the difference um, between breadth first search is that breadth first search now goes level by level. So, we'll scan this level, then we'll scan on this level, and then we'll scan on this level, right? That is how breadth-first search works, and it uses queue, the queue data structure, right? It uses the queue data structure to enable us achieve what we want to achieve. Um, it's really simple to implement, but due to how long this stream has gotten, it's almost 1 hour 30 minutes. It's about 1 hour 16 minutes. I've been talking non-stop. Um, would have a part two for this, and that part two is likely going to be like a pre-recorded video, or probably it's going to be kind of like another life, but it's going to be a really short life. But the summary of what a binary first search is that it uses the queue, right? So that is a vec DQ on Rust. I think. When we talked about queues, we did something like that. So that is vec uh, DQ Rust. So I think we also implemented queues here. Where is that? So this is it. So in our past lectures, sorry, tutorials or live streams, we use this guy, right? VecDQ. So it's coming from the standard library, collections and VecDQ, right? So this is like what would use to do the, breadth first search and stuff that will move from level to level, right? So yeah, so looking at the documentation, we have the VecDQ, which is in the standard library and in collections. So we have things like the pushback that adds nodes to the back of the queue, and the pop front that removes from the front of the queue. So I explained this in our queue when we had the live stream for queues, how queues work, right? Where we enqueue, we add items to the back of the queue, and with the queue where we remove elements from the front of the queue, similar to like when you you know, visit an ATM or you go to the bank or something. I think we went ahead to we built a music playlist. Yeah, we built a music playlist with this, right? So let me just go on YouTube and see. I think we did something like that. YouTube. mm, Okay, I'll just pause this. Um, I don't know. My channel. We did something that had to do with a playlist. I think this is it. So we made this video where we